This is part C for our unit on exploratory factor analysis. And the next thing I want to talk about is rotation. So first, let's review what we've talked about up to this point. We've talked about the process of extracting factors or extracting components out of a set of items, and how we can go through and extract the maximum number possible of components that we can extract, which is equal to the number of items. So if I have a 6-item questionnaire, the maximum number of factors or components that I can extract is 6. And my first step would be to go ahead and extract all 6 factors or all 6 components from that data set. And then I would look at those results and decide how many factors or components I really need. And then I would go back and extract only those factors or only those components that I really need. So if I had a 6-item questionnaire, I would first extract all 6 factors. And then I might look at that and say, well, based on theoretical judgment, based on the number of eigenvalues greater than 1, based on a scree plot, or maybe based on a parallel analysis, or some combination of all of those, I might decide, well, I think I only need 2 factors. I don't need all 6. I only need 2. So then I would go back and extract only the first 2 factors, and I would stop there, and I would have my 2-factor solution. So now at this point, I want to look at the results. Specifically, I want to look at those loadings, my pattern matrix or my structure matrix, which are both the same thing, that matrix of factor loadings that I have for just my 2-factor solution. And when I look at those loadings, I want to make an interpretation about which items load on which factors. I want to come to some conclusion about these items all seem to load high on this factor, and these other items all seem to load high on another factor. And I want my solution to be something that I can easily interpret. The problem is that usually when I do this, if you take the first 2 factors you extract and look at the solution, oftentimes it's not easy to interpret. Part of the problem is the fact that recall that the first factor will explain as much possible variance as it can, and then the second factor will explain variance in the leftovers, the stuff that couldn't be explained by the first, and the third factor will explain stuff in the leftovers, the stuff that couldn't be explained by the first 2 factors. So each successive factor is explaining less and less variance, which also means that each successive factor is becoming less and less important. And what I really want is to have factors that are all essentially equal in importance and ones that I can interpret equally well. And so to deal with this, we're going to do something called rotation. And rotation is a process where we're going to take a solution. We're going to take a matrix of factor loadings or of component loadings, if you want to be precise in our language, and we're doing principal components analysis. We'll take our matrix of loadings and we're going to do something called rotation. And the purpose of rotation is to try to make our solution easier to interpret. So we're trying to get at a solution, we want to get a set of factor loadings that are easy to interpret. And oftentimes when we extract the number of factors we want to extract and look at our solution, it's often not very easy to interpret initially. So we're going to do something called rotation to try to make it easier to interpret. And when we do rotation, there's 2 basic processes we can use. So one option, we could simply not rotate our solution. And if we don't rotate it, it would be hard to interpret. I've actually never seen anyone do a factor analysis and not rotate it. But that is one option. We could just take our initial solution and not rotate it and try to interpret that. So the 2 options for rotation are to do something called orthogonal rotation or oblique rotation. And we're going to talk about those next. One type of orthogonal rotation that's the most common is something called Varimax rotation. And if you're using SPSS to do data analysis and you want to do oblique rotation, the option you would select there is usually something called direct Oblique, I think is how you pronounce that, is a type of oblique rotation. So we're going to talk about rotation. Rotation is something we will use to try to make our matrix of factor loadings or component loadings, to try to make that matrix of loadings easier to interpret And we're going to do that either using orthogonal rotation or oblique rotation. So let's start by looking at results from a factor analysis that are not rotated, and then we will eventually rotate these results and see what happens when we use rotation. So in this example, it's from a study where I gave a questionnaire to people who were in romantic relationships, asking about their experiences of having a conflict with a romantic partner and what types of emotions they experienced during that conflict. And I have results here from 6 items on a questionnaire. So one item was asking about, during this conflict, how much did you feel angry? And another item asked about how much did you feel irritated and how much did you feel annoyed? And did you feel hurt? Did you feel concerned? And did you feel sad? So I have 6 emotion items asking about the feelings that people experienced during a conflict with a romantic partner. And theoretically, I would think that my first 3 emotions, angry, irritated, annoyed, are things that I might call hard emotions that involve asserting one's own rights and standing up for oneself. And when people express hard emotion, they might be viewed as being threatening or hostile. And when people express hard emotion, partners might want to defend themselves against it. In contrast, hurt, concern, and sad might be what I would call soft emotion, that involves more expressions of vulnerability. And sometimes when one person expresses soft emotion, it might elicit empathy from a partner. So both hard and soft emotion are types of negative emotion that people might experience during conflict. But there should be some differences between hard emotion, which involves more assertiveness and interest in trying to stand up for one's own self-rights, and soft emotion, which involves some expression of vulnerability. So in this analysis, I had my questionnaire with 6 items, and I put it into actually a principal components analysis. And recall the very first step, I'm not showing it here, but the very first step, I extracted all 6 components, or all 6 factors, because I have a 6-item questionnaire, so the maximum number of components I can extract is 6. So I first extracted all 6, and then I looked at the results to try to decide, how many factors do I really need? Do I need all 6? Do I need 1, 2, 3, 4, 5, 6? And I decided I really only needed 2 components, or 2 factors. So then I went back and did an analysis where I extracted only the first 2 components, or the first 2 factors. And then I got the factor loading matrix, or the component matrix. And we have SPSS output here, and it's giving me the precise terminology here. It's noting that it's a component matrix of the component loadings, or the factor loadings. And that's the same thing. This would be the same thing as the pattern matrix or the structure matrix. Both of them are going to be the same thing. The pattern matrix, if we use each component or factor score to predict each item, and the beta weight for that, the standardized beta weight, if I use each component or factor to predict each item, is the what I would get from the pattern matrix. Or the structure matrix is the correlation between each component or each factor and each item. And in this case, both the pattern matrix and the structure matrix are the same thing. Although, by the way, in just a moment, I'm going to give you an example where we need to distinguish between the two. So that's going to become an important difference in just a moment here. But for right now, the pattern matrix, structure matrix are the same thing. We could just call it our matrix of factor loadings or our matrix of component loadings, which SPS is labeling our component matrix right here. Let's think of these in terms of correlations for now. And note that, so we'll say that here this 0.81, we can talk about that. The usual way of talking about this is to say the item angry loads on our first factor or our first component. The loading is 0.81. The loading for item 2, how much feeling irritated, loads on component 1. That loading is 0.768. The loading for our third item, how much our third item feeling annoyed, loads on our first factor component is 0.76. And so the way people usually talk about this is to talk about these as the factor loadings. And so we can look at how do the items load on component 1 or factor 1 and load on component 2. Now, what we would like to find is something called simple solution. And a simple solution is where each item has a really high loading on one and only one factor, and each item loads low on all the other factors. So what I'd be looking for here is a situation where if I think angry, irritated, and annoyed are all types of hard emotion, should all load on one factor, I'd be looking for a type of simple solution where angry, irritated, and annoyed all have really high loadings on one factor and low loadings on another. And I'd be looking for a solution where hurt, concern, and sad all have high loadings on a different factor and low loadings on everything else. This solution here is a little bit hard to interpret because our very first component, it seems like all 6 of these items have very high loadings on that first component. Now our second component seems to be teasing apart the difference between our hard emotions, which have negative loadings, and the soft emotion, which has positive, but it's hard to give our factors names this way, because usually what we want to do is we found that all the hard emotion items, so if my ideal situation, say if all the hard emotion items loaded on my first factor and all my soft emotion items loaded on my second, I would say this first factor is the factor for hard emotion, and all the hard emotions load on that. And the second factor is the factor for soft emotion, and all the soft emotions load on that. That would be the ideal situation, but that's not what I have here. This is kind of a confusing thing where I have my first factor is just kind of overall stuff, I guess, overall negative emotion, that all the items load high on that. And then my second factor is the tease apart distinguish factor, where the hard emotions have negative and the soft emotions have positive loadings. So this is a little bit hard to interpret. But to illustrate the concept of rotation, I want to plot this matrix, this table of factor loadings or component loadings. I want to plot it in two-dimensional space. And actually, I've specifically chosen an example where I have just 2 factors, because if I have 2 factors, I can plot it in two-dimensional space. If I had 3 factors, I need to use 3-dimensional space. And if I had 4 factors, I need to use 4-dimensional space. And that gets more and more tricky. So I've intentionally chosen an example that only has 2 factors, because that can be plotted visually in 2-dimensional space. Mathematically, we can rotate 2, 3, 4, 5, any numbers of factors, but if I want to look at it visually, it's much easier if I limit myself to 2 factors, because we can look at that in 2-dimensional space. And that is what I've done over here on the right. So I have this x-axis is labeled component 1, and the y-axis is labeled component 2. And I should have put numbers in here. I realize I haven't put numbers on my axis, but we can label these. I think it was 0.2. So if we put this, I think that should be 0.2, 0.4, 0.6, and 0.8. And this will be negative. Negative 0.2, negative 0.4, negative 0.6, and negative 0.8. And then the same component 2 will be labeled the same. I'd have positive 0.2, positive 0.4, positive 0.6, and positive 0.8. And down here will be negative 0.2, negative 0.3, negative 0.3, negative 0.6, and negative 0.8. And these are going to be sizes of correlations. So what we'll do here, we'll look over at a table, and what's the correlation between component 1, or factor 1, and the item feeling angry? The correlation is 0.8. What's the so for component 1, here's item angry. Here's component 1, item angry correlates 0.8 with component 1. Item angry correlates negative 0.42 with our second component. So I'm going to go down here to 0.42 on our second component. Negative 0.42 would be right about there. So I put a dot right here for feeling angry, and that dot is at it's at 0.81 for component 1, for this component right here, and it's at negative 0.42 for our second component, for that component there. So I'm just plotting where the item angry falls in this two-dimensional space based on what's the correlation with component 1 and what's the correlation with component 2. And then we'll do the same thing for other items. For example, let's look at hurt. Hurt had a correlation of positive 0.829 with component 1. So here's hurt, and that had a positive correlation. That would be, again, that's our 0.8 with component 1. And I had a correlation of positive 0.3 with component 2. So that would be right here at 0.31 with component 2. And so I put a dot right here for hurt. Or let's look at concern. So concern had a little bit lower correlation. It was only correlated 0.6 right here. That would be 0.6 with component 1. And its correlation with component 2 was up at a 0.556. So right here, that would be at a 0.55. So I'm plotting where each item falls in two-dimensional space based on the correlation it has with component 1 and component 2. And this picture right here shows this two-dimensional space with no rotation. And the idea of rotation is this, is that I can take this XY axis and I can turn it. I could say turn it this way, and I could rotate it, and it would still be describing the same two-dimensional space. There's no arbitrary rule that this XY axis has to go straight up and down and side to side. I could turn this axis different ways. I can rotate it and still represent the same two-dimensional space. So let's see how this might work. So now this is showing you a rotated solution. Note that my dots for concerned and sad and hurt for all my items are still in exactly the same place in two-dimensional space. They have not moved at all. However, I've rotated this XY axis, I've rotated it. So now component 1 is on an axis from the upper left to the lower right, and component 2 is on this axis from the lower left to the upper right. So let's look at where our items fall when we define our two-dimensional space, not with a vertical and horizontal axis, but with these diagonal axes going this way. So now let's look at concerned, for example. It falls right here. So in component 2, it's really high on component 2, and here's concerned, and it actually is at 0.83 on component 2. It's 0.83. But on component 1, it's really low on component 1. Actually, it's at 0.087 on component 1. Or, for example, hurt. Let's see what that's doing here. So we've got hurt is at 0.787 here on component 2. And it's a little bit higher on component 1. It's at a 0.406 on component 1. And this was a 0.787 on component 2. Or if we look at angry, now angry had a really high score on component 1. So angry had a score of 0.89 on component 1, and somewhat of a lower score on component 2 at 0.235. So note that when I rotate my axes here, when I have this XY axis and I rotate it, where my items sit in two-dimensional space still stays exactly the same. But all my loadings in my matrix over here, they all change to reflect this new organization of two-dimensional space. And now, if we look at these loadings, note that we're getting something that approaches more of a simple solution. It's approaching more of that solution that I wanted, because I have angry, irritated, and annoyed, my heart emotions. They all have loadings of 0.8 and higher, pretty high loadings on component 1. And they all have kind of low loadings, 0.2 around that, all less than 0.3. So they all have relatively low loadings on component 2. In contrast, my 3 soft emotions, they all have relatively high loadings on component 2. And some of these, they're a little bit high, but for the most part, these are kind of low loadings on component 1. So I'm getting something that's approaching a pretty nice, simple solution here, where I can say component 1, or factor 1, if I want to use more loose language, that factor 1 is the factor representing hard emotion, And for the most part, the hard emotion items have high loadings on factor 1, and the soft emotion items have weaker loadings on factor 1 or component 1. And I would say that factor 2 or component 2 is my soft emotion factor, and all the soft emotion items tend to have higher loadings on that factor, and they tend to load weaker on component 1. And so that is the type of solution we can interpret. And with this type of interpretation, it's a way of looking at items and saying, what factor does it load on? And we get a theoretically meaningful solution here where items load on factors that make theoretical sense. So what we're doing here is trying to figure out what factors items belong to by having a solution where each factor has a high loading on one factor and low loadings on all the other. And when we do that, we call that a simple solution. That's what we're trying to get. And we're better able to get that when we do rotation. Now, I'm going to call this orthogonal rotation because when I rotated, recall that orthogonal means at right angles. And so my x and y axis are at right angles to each other, showing two components that have a zero correlation. Component 1 has a zero correlation with component 2. Or if I want to use loose language, factor 1 has a correlation of 0 with factor 2. And so these two components, or the two factors, are orthogonal. They have a zero correlation. And I represent that by keeping this x and y axis at right angles. And when I keep them at right angles, that means that I'm keeping it at a zero correlation. Now, one thing you might be wondering, if we're going to do orthogonal rotation, how do we decide how far to rotate the axes? If we rotate it just a little bit, we could just, if we have it like this, if we rotate it just a little bit, or maybe we go just a little bit, or we could go like this, or we could go like this. How do we decide exactly where we rotate it to? And the most common way of doing orthogonal rotation is to do something called Varimax rotation. In fact, it says Varimax right down there. Varimax rotation. And what that is a process of rotating the x and y axis so that when we calculate the percent of variance explained by component 1 and by component 2, or the percent of variance explained by factor 1 and factor 2, note that normally when we have an unrotated solution, the first component explains the most variance and the second component explains less. And if we had more, then each successive component would explain less and less variance. And what we want to do is rotate so that the variance explained by each component, or by each factor, if we're doing factor analysis, so that the variance explained by each component is as evenly distributed as it possibly can be. So I want to try to get to a situation where the percent of variance explained by component 1 is about the same. We can't make it perfectly equal, but I want to try to find some rotation that will make it so that the variance explained by component 1 is very similar to the variance explained by component 2, so that each component that I've extracted explains about the same amount of variance in my x variables. And so when we do orthogonal rotation, what the computer is going to do, it's going to rotate that x and y axis and try to find which rotation will best distribute evenly the variance explained across the different components that you have in your analysis. And that is how you do orthogonal rotation. So now here is an example of what happens if we do oblique rotation. So with orthogonal rotation, when we rotated our x and y axes, we forced them to stay orthogonal. We forced the correlation between factor 1 and factor 2, or component 1 and component 2. We forced the correlations to stay at 0, to be orthogonal. Now with oblique rotation, we're both going to rotate our axes and allow those axes to correlate with each other. And when we do that, that comes out with not forcing them to be at right angles. So note that here now I've rotated things, and I've rotated it so that this component 1 is going more directly right through these hard emotion items, and component 2 is going right through these soft emotion items. And that will make my results even easier to interpret. And essentially what we do with orthogonal rotation, we're rotating with an assumption that the correlation between my factors needs to be 0. When I do oblique rotation, I'm thinking, well, it's not really reasonable to assume that my factors are going to have an exactly 0 correlation. In real life, when we measure things, we don't expect to measure different components or factors, dimensions. We don't expect those things we measure to have an exact 0 correlation with each other. Most of the time we measure things, they are correlated. So it's more reasonable, if we're going to rotate our solution, to also allow our axes to correlate with each other. So I've no longer forced my x and y axis to remain at right angles. I've allowed them to become a little bit oblique, and that's showing a degree of a correlation between the two. So now at this point, though, my pattern matrix and my structure matrix are no longer the same thing, because my pattern matrix gives me what is the effect of component 1 or factor 1 predicting scores on items controlling for factor 2. And when my two factors or my two components, when they were orthogonal, the effect of one component controlling for the other was the same as that component by itself not controlling for the other. It didn't make a difference if I controlled for the other component or not, because my two components didn't overlap. They were not correlated. But now with oblique rotation, I'm allowing my two components to correlate. And so now the pattern matrix, the effect of each component predicting an item controlling for the other component, is not the same as my structure matrix, which is the correlation between the component and the item without controlling for the other component. So the pattern matrix is going to give me the unique effects, the extent to which each component explains unique variance in an item controlling for the other component or the other factor. And the structure matrix is going to give me correlations, the extent to which each component or each factor correlates with each item without controlling for the other component or the other factor. And so in general, my pattern matrix loadings are probably going to be a little bit smaller, and my structure matrix loadings might be a little bit bigger, and my pattern matrix is probably going to be a bit cleaner because it's only showing me that unique variance, the extent to which each component explains unique variance in an item, and I'm pulling out the overlap between my two factors. When we do an oblique rotation, we will get both a pattern matrix and a structure matrix is a common part of the output, and we can look at both. It's most common to focus on interpreting the pattern matrix. So if I was reporting results in a journal, I would probably only publish the results for the pattern matrix because that's the most common one to report. So let's look at these two, see what we get here. So note that when we're doing oblique rotation, now we're getting, especially if we look at our pattern matrix, now our results look really easy to interpret, and they're really nice and clean. We get a clear, simple structure here. We see that angry, irritated, and annoyed, again, they all have really high loadings on component 1. So here's angry, irritated, and note that because we have rotated in a way that now they just sit right on top of that component. So now we've got 0.9, 0.88, 0.8. So we got really high loadings on component 1, and they have almost 0 loadings on component 2 or factor 2. And in contrast, hurt, concerned, and sad, my soft emotion items, they all have really high loadings on component 2 or factor 2, if I want to use more loose language. And the loadings on component 1, these are all really small, 0.2, a negative 0.13, 0.01. So we got small loadings there. So this is a good example. This is clearly what I would call a simple solution, a nice clean result where each item loads really high on one factor and only one factor or one component, and loads low on the other component. If we look at our structure matrix, it's not quite as clean because this is looking at our correlations so that we see how much overlap there really is. So we still have our hard emotions load really high on component 1, but if I'm looking at correlations without controlling for component 1, we see that angry, irritated, and annoyed really are somewhat still correlated with component 2. We have some moderate correlations there. And likewise, our soft emotion items still have really high loadings on component 2, but we see they actually do have some notable correlations here with component 1 as well. Now, another thing that happens when we do oblique rotation is that because our components or our factors, because they're now correlated, it's reasonable to ask, well, what is that correlation? To what extent is factor 1 correlated with factor 2? Or if I'm doing principal components analysis, to what extent is component 1 correlated with component 2? And here we have output here, which shows the correlation. The correlation between these two components is 0.48. So we've got a moderate, almost a large size correlation between our two factors or our two components. In other words, when people have hard emotion, the extent to which they have hard emotion tends to be correlated with the extent to which they're also experiencing soft emotion. These are two types of negative emotion, and sometimes people experience both. If someone's having a conflict, it's common if they have high hard emotion, they might also have some degree of soft emotion. If they have high soft emotion, they might also have some degree of hard emotion. These two things are correlated with each other, and the correlation between these two factors, or these two components, is 0.48. So when we do oblique rotation, we now have both a pattern matrix and a structure matrix. These are now two different things. It's most common to interpret the pattern matrix, and we'll have a correlation between our two factors or between our two components, and it's important and common to report what that correlation is. Now, let me summarize some of the things I've been talking about. So we've been comparing different options for rotation. We talked about we could do no rotation, orthogonal rotation, or oblique rotation. And one of the key questions is, do we want to allow our components or our factors to correlate? If we do no rotation, we will have orthogonal factors or orthogonal components. They will not be correlated. And of course, if we do orthogonal rotation, our factors or components will not be correlated. But if we do oblique rotation, then the key difference there is that now our components or our factors, they will be correlated. And that's the key feature of oblique rotation. And to summarize further, when we do oblique rotation, our components or factors are correlated. Therefore, the pattern matrix, which is made up of beta weights, will not equal our structure matrix, which is based on correlations. And our pattern matrix is the one that indicates the unique effect explained by each factor. How much does each factor or component explain unique variance in the items after controlling for the other factor or the other component? And the pattern matrix will generally look cleaner. It will come closer to providing a simple solution than will the structure matrix. And the pattern matrix is the matrix that is most commonly reported when you report your results, say, in a journal article. And finally, when you do oblique rotation, it is of interest and it is important to calculate the correlation between your components or factors and to report that correlation. Now, I want to call attention to the fact that when you do rotation, that rotation is going to change the meaning of the sum of the squared loadings. That is what we were calling our eigenvalues. So this is showing you the results we were looking at previously in this unit, where I had a data set with 4 items, and this is where we extracted all 4 components, or all 4 factors. And recall, if we took the sum of the squared loadings for factor 1 or for component 1, we got an eigenvalue of 1.7. If we summed all 4 squared loadings for factor 2 or component 2, we got an eigenvalue of 1.8. And for factor 3 or component 3, we got 0.76 and 0.24. And we saw how if we sum our eigenvalues, if we extract all the possible factors or components that we can extract, then the sum of our eigenvalues will equal the number of items on our instrument. And so we have 4 items, so the sum of our eigenvalues equals 4. And then if we take each eigenvalue and divide by the number of items on our instrument, we get the percent of variance explained by that component or by that factor, how much that factor explains variance in all of our items. And so we saw that our first factor, our first component, explained 44.25% of the variance. The second one explained about 29%. The third one explained about 19%. And the fourth explained a little more than 6%. And if you add up all those percentages without rounding, which I've rounded here, but if I actually did it without rounding, it would add up to exactly 100% of the variance would be explained if I extracted all four of my components, if I have 4 items. So what I want to focus on here is the sum of the squared loadings, the eigenvalues that I get when I sum the squared loadings for each component or each factor. And note that this example here is when I'm extracting components or factors and not doing any rotation. But if I do rotation and sum squared loadings, I'm going to get stuff that means something different. So let's see what happens when I do different approaches to rotation and how that changes what we have for what eigenvalues or what the sum of the squared loadings are. So this table summarizes what happens with different types of rotation when we look at the sum of the squared loadings. So we have at the top here is a column for if we do no rotation, then a column for if you do orthogonal rotation, and then a third column for if you do oblique rotation. And first, let's just think about terminology. What do you call the sum of the squared loadings? We saw that in the example with no rotation, I called it an eigenvalue. So the eigenvalue is if you go down the column of loadings for a factor or component and square all the loadings for that component and sum those squared loadings, you call that an eigenvalue. And I just want to note that if you do rotation, we're no longer going to call that an eigenvalue. We will simply call it the sum of the squared loadings. So with no rotation, the terminology is the sum of the squared loadings is called an eigenvalue. But if you do rotation, either orthogonal or oblique rotation, the sum of the squared loadings is simply called the sum of the squared loadings. I won't call it an eigenvalue anymore. I'll just call it the sum of the squared loadings. Now, what about the issue about how the sum of the squared loading, the size of those loadings, how does that change across factors? We saw that when I did no rotation, each successive factor explained less variance. The eigenvalue got smaller and smaller with each successive factor. Each successive factor explained less variance in all the x variables in all my items. So my sum of squared loadings, the size of my sum of squared loadings, decreased with each successive factor. And that was true when I did no rotation. But recall I mentioned a moment ago that when we do orthogonal rotation, and actually this is true for oblique rotation as well, the goal is to try to find a rotated solution that will distribute the percent of variance explained by each factor or each component. We'll try to distribute that explained variance relatively evenly, at least as evenly as possible, across your different factors. The goal is to try to get a solution so that each factor or each component will explain approximately about the same amount of variance in the items. So when you do rotation, and again, it doesn't matter if you do orthogonal or oblique, your sum of squared loadings will be relatively evenly distributed across your factors. Whereas if you do no rotation, that sum of squared loadings will decrease with each successive factor. So now let's consider what do you get if you sum all those squared loadings. We already saw that if you extract all the possible factors that you can extract, so if you have 6 items and you extract 6 factors, if you have 24 items, you extract 24 factors. So if you extract the number of factors or the number of components that is equal to the number of items that you have, you will have extracted all the possible factors or components that you can extract. You can't extract anymore. You will have explained 100% of the variance in the items, and the sum of all your sum of squared loadings, if you sum across all factors, will equal the number of items. Let's back up to our previous slide here. Recall that here, I was trying to erase stuff. There we go. That if we have 4 items, we extract 4 factors or 4 components. The sum of our eigenvalues for each factor will equal the number of items that we have. So if I have 4 items, the sum of all my eigenvalues will equal 4. And that will be true both when you do no rotation and if you do orthogonal rotation. That will still be true. If you do orthogonal rotation and extract all the possible factors or components that you can extract, it will still be true that the sum of all your sum of squared loadings will still equal the number of items. But if you do oblique rotation, it doesn't make any sense to sum across all your sum of squared loadings. You will just get some kind of meaningless value. It won't produce anything that we can interpret or do anything with, and it will definitely not equal the number of items that you have. So if I'm doing oblique rotation, I would simply not do that. I would simply not sum across all the sum of squared loadings for all my factors or across all my components. So if I do oblique rotation, it would just give me something meaningless. And recall that before, with our original example with no rotation, we calculated an eigenvalue and then divided it by the number of items to get the portion of total variance that was explained by that component or by that factor. Let me back up to our previous slide. And so we saw that, for example, factor score A explained 44% of the variance, factor score B explained 29%, factor score C explained 19%, and so forth. So we took each eigenvalue, divided by the number of items, and we got the percent of variance explained by that component or by that factor. And we can do that both with, if I'm doing no rotation and if I'm doing orthogonal rotation, I can still do that. Now with orthogonal rotation, that percent of variance explained by each factor is going to be distributed differently across my factors. It's going to be more even, whereas if I do no rotation, the percent of variance explained by each successive factor is going to be less and less. But either way, we can do that. We can take our sum of squared loadings divided by the number of items, and we can interpret that as a proportion of variance explained by that factor or by that component. However, if I do oblique rotation, I cannot do that. If I take my sum of squared loadings divided by the number of items, I get just some meaningless value that doesn't tell me anything. So if I'm doing oblique rotation, it doesn't make any sense to calculate the sum of all the squared loadings, and it doesn't make sense to take a sum of squared loadings and divide it by the number of items. That makes sense if I'm doing orthogonal rotation. That still would give me meaningful information. With oblique rotation, that no longer gives me meaningful information. So that is comparing what happens to our sum of squared loadings if I do no rotation, orthogonal rotation, or oblique rotation, and seeing how we interpret the sum of the squared loadings differently depending on what type of rotation we're doing. Here are the results for that example we've been using throughout this unit, where I have a sample of 20 people and items from just 4 items on a questionnaire. And up at the top, I show you the results that we've seen this before, where our eigenvalue for our first component was 1.77, for our second component was 1.18, 0.76, and 0.226. And the first component or the first factor explained 44% of the variance, the second one explained 29%, and so forth. And the thing to note is that, and we've seen this before, I've already shown this to you, but note again how the eigenvalues decrease with each successive factor. The sum of the eigenvalues sum up to 4, and we can look at the percent of variance explained by each factor, and the percent of variance explained decreases with each successive factor we extract. And if I extract as many factors or extract as many components as I have items on my questionnaire, if I extract the maximum number of components or factors, then the sum of my eigenvalues will add up to, the sum of the percent of variance explained for each factor will add up to 100%. I will explain 100% of the variance in my items. Now let's look at what happened if I take this exact same data set, the exact same example, and now I'm going to do an orthogonal rotation. I'm going to ask the computer to do actually that Varimax rotation, where it will try to come up with a rotation that will distribute the percent of variance explained more evenly across my factors. And again, with rotation, we're going to end up evenly distributing variance across factors. So first, let's look at our now this would be the sum of the squared loadings. We called this eigenvalues before, and now I'm simply going to call it the sum of the squared loadings. So the sum of the squared loadings for component 1 or factor 1 was 1.02, then 1.01. It's not identical, but pretty close. Then 1.0, and then 0.97. So these are really, really close. They're not identical to each other, but it comes much more evenly distributed, where it went from, up here it went 1.7 to 1.1 to 0.76 to 0.26. So there was a big decline in our eigenvalues with no rotation. And now the sum of the squared loadings with orthogonal rotation are very, very similar to each other. But still, if you sum these up, the sum of these sum of squared loadings still sum up to a value of 4. So with no rotation or with orthogonal rotation, either way, you sum the sum of the squared loadings and you get a value of 4. Because we have 4 items, then the sum of the squared loadings equals the number of items, 4. And if, again, I've extracted as many components or as many factors as I have items, so I'm going to explain 100% of the variance. So here's the percent of the variance explained by my first factor, or my first component, about 25%. The second factor explained about 25%. The third explained about 25%. So all my factors, or all my components, are explaining about 25% of the variance. And if we add it up, it adds up to 100%. So again, it's more evenly distributed across my factors, but it still adds up to the same percent of variance explained. Now at the bottom, we have oblique rotation, and as with orthogonal rotation, our sum of squared loadings are evenly distributed, at least as evenly as possible. They're more evenly distributed across the 4 components, or the 4 factors, 1.4, 1.18, 1.2, 1.4 again. So we have a relatively even distribution of values across of our sum of squared loadings. Those are relatively even. They're similar across our 4 different factors, or 4 different components. But everything else is now different. So we can't sum these and get something meaningful. If you sum 1.4 plus 1.18 plus 1.23, it does not equal 4. So the sum of the squared loadings no longer equals the number of items. And I did not even take this is all blank down in here, and that's intentional because if I took my sum of squared loading and divided by number of items, if I took 1.4 and divided by 4 and put that value here, that would just be a meaningless value. It wouldn't give me any useful information. I don't know what it would mean. I could take a 1.8, divide that by 4, but I don't know, that wouldn't give me anything meaningful. So I left this all blank here because it would not be meaningful to take a sum of squared loading and divide by number of items if I'm doing oblique rotation. And if I did that, even if I did that, I would get meaningless values. And if I summed it all up, it would not equal 100% with oblique rotation. It would not give me anything meaningful. So with oblique rotation, I'm not going to do anything where I divide my sum of squared loadings by number of items, and not going to be talking about using values from the oblique rotation to talk about percent of variance explained. If I do oblique rotation at that point, I can't really talk about how much variance in my items was explained by each factor or by each component. Now, one more thing that changes depending on what you do with rotation has to do with the communalities. So just a moment ago, we were looking at eigenvalues, or the sum of the squared loadings for each factor or for each component when I do a factor analysis. And we saw how those sum of the squared loadings, or the eigenvalues, mean different things depending on how you do rotation. And recall that the eigenvalues, or the sum of the squared loadings, are where we're summing down columns in our matrix of factor loadings. We have one column for factor 1, and a column for factor 2 or component 2, and a column for factor 3, and we're summing down columns to get a sum of squared loadings for each factor. The communalities are where we're going to be summing across rows to get a communality for each item, and we'll sum across the squared loadings for each item to get its communality. And I talked about the fact that if we do no rotation, At least that's the example we've been using. With no rotation, we saw how if I extract the maximum number of components or the maximum number of factors, so that the number of components or factors that I extract is equal to the number of items, at that point, my factors will explain 100% of the variance in each item. So if I calculate the communality after extracting the maximum number of factors or components, the communality will be 100% or 1. So in this example here, these are the component loadings or the factor loadings when I extracted all 4 factors from our example where we had a 4-item questionnaire. And so if I take the loading for x1, 0.79 squared, plus for factor 2, 0.47 squared, plus negative 0.23 squared, plus 0.32 squared, and sum it up, and if I didn't do any rounding and had the actual unrounded values here, everything would sum up to exactly 100%, to 1. My communality for x1 would be 1, my communality for x2 would be 1, my communality for x3 would be 1, and so forth. And that will still be true if I did orthogonal rotation. So with both no rotation and orthogonal rotation, I can still sum across my my squared factor loadings for an item and get a communality. And if I extract the maximum number of factors or components, my communality will be 1. With oblique rotation, that's no longer true. If I extract the maximum number of possible factors or components that I could extract and sum across my squared loadings for an item, it will not equal 1. And I cannot really interpret the sum of the squared loadings as communalities. They're not exactly the same thing anymore. So if we ask the question, does the sum of the squared item loadings, so we're not going summing down for a factor as we did for calculating eigenvalues and sum of squared loadings. Now which is confusing because these are both sums of squared loadings. But when the thing we label sum of squared loadings is when I'm summing down the column to get the loadings for a factor. Now I'm summing the loadings across a row. And if I do that with no rotation or orthogonal rotation, I won't call it the sum of the squared loadings. I'll simply call it the communality. So the communality is the sum of the squared loadings across a row. But if I'm doing oblique rotation, I simply wouldn't do that. That would not give me a meaningful value. So the question, does the sum of the squared loadings for items, the sum of the squared item loadings, does that equal the communality? If I'm doing no rotation, yes it does. If I'm doing orthogonal rotation, yes it does. But if I'm doing oblique rotation, no, it doesn't. It doesn't give me something useful or meaningful. I would not do that with oblique rotation. And now we have finished everything about principal components analysis, and we are ready to move on to actual factor analysis. And I will put that in the next video.